know you're not pouring.
And you all get on the side, you like 5 to 6.
I haven't, yes, I did, so I did have a slight mistake. So I had to bid, and then you're okay. I don't know what the fuck I was supposed to do. 5 minutes, I don't know. Yeah.
Okay. So, yeah,
I have an announcement.
sure.
Today at the men's soccer game at halftime, there's a competition, like a crossbar challenge. So if you come and you can kick the soccer ball, kick a crossbar, there's a bunch of prizes for you to win. So if you're interested in winning some free stuff, comment down.
Is that a home game or is it a
Yes,
game?
it's a home game. The kickoff is at 3, so halftime, assuming not too many stoppages, should be around 3:45. So you can come just for that 5 minutes, or you can come for the whole game.
All right. Go show off, everybody. Awesome. Any other announcements from the class? We can have announcements. I like that. Sounds good. Okay. So I'm going to start by quick recapping what you hopefully all watched on Friday when we didn't have class. Mainly going to focus on this membrane transport part. The very final bit that you did in metabolism was really meant to briefly understand what's going on with fat, right? And the big takeaway there is that through this process of beta oxidation, we can store a lot of energy in triglycerides because we are storing a fair amount of energy in those fatty acid tails, in those tiny little chunks of the carbon-hydrogen bonds. So any individual little chunk in a fat molecule, in a lipid like a triglyceride, isn't going to give you quite as much as a glucose molecule. But because we have such long fatty acid tails, if you take a triglyceride as a whole, there's tons and tons of energy. And that's the big picture point about fat. That's why fat is good for long-term storage, because you're packing lots of energy into kind of tight space, into kind of efficient vehicle for storage. Okay. So that was the end of the last packet. And what I had you mainly reviewing, hopefully, from your previous courses was the structure of cell membranes, right? So you remember that hopefully in the fluid mosaic model, we have this idea that our cell membranes are composed of many different types of molecules, but particularly we're starting with a phospholipid bilayer. It's got stuff inserted in it, cholesterol to kind of stabilize it, membrane proteins for lots of different purposes, but for our class, the most important thing to know about membrane proteins is the fact that a bunch of those membrane proteins act as transporters and channels. So they're going to be allowing things to cross membranes. That's really crucial. We're going to see them close, open, change shape, all sorts of stuff in this class. And we also have some little pieces of carbohydrates kind of hanging off stuff. So we reviewed the structure of the phospholipids and what they do and how they lead to this permeability of the membrane, how they make it so that nonpolar molecules, small little nonpolar molecules especially, are able to get across the phospholipid barrier because they have this kind of hydrophobic nonpolar quality. But things with charges and anything that's too large is blocked by this double layer of phospholipids. Okay, so we also mentioned cholesterol exists. Cholesterol exists. It's a type of lipid. You can recognize that steroid kind of basis of the structure. We looked at proteins and saw some of their functions, in particular, the fact that integral membrane proteins embedded in the structure sometimes go all the way across. Those are our transmembrane proteins, and they're really, really important in this class because they're what's going to allow for transport, in particular, of things like ions and things like glucose. we're going to need membrane proteins to get through those. They also do other stuff. We'll see receptors, we'll see enzymes. We'll talk about them when we get there, but those are also proteins. There are some membrane proteins that are just stuck on one side of the membrane or the other. We call those peripheral membrane proteins. We got little carbohydrates, kind of mostly for like cell recognition stuff, tacked on to some of our lipids, some of our proteins. And we thought a bit about the purpose of the cell membrane, right, and how it acts. Okay. So our membranes are separating the inside of the cell from the outside of the cell. So the ICF, the intracellular fluid, from the ECF, the extracellular fluid. This is important because we want to control the passage of materials between these two fluid pairs, right? So those were two of our kind of buckets of where we find water in the cell, right? When we broke up total body water in the first week, those were two of the places we were focusing on. We want to control the concentrations and in general, the composition of fluid inside the cell versus outside the cell. Okay, so you saw a little bit about what can and can't cross a membrane and reviewed that. Okay. And then we began our discussion, and hopefully this is a reminder of gradients. And this is what's building us to the topic of our electrochemical driving forces eventually. So that's the topic in this first unit, in this first exam, that I actually expect to be kind of completely new to you. So most of the rest of this to this point should have been kind of a review. Now we're getting to the new stuff, and we're going to see some numbers that we're actually going to be playing with. So it's important to make sure that we're building to this little bit by little bit, getting each step along the way. Okay. So when we're thinking about transport, we're going to be thinking about gradients, and we're going to be thinking about forces. What we're thinking about is what direction do molecules move with respect to our cell, right? Do they go in? Do they go out? And does this take energy, or is it spontaneous? Is it easy? All right. That's fundamentally what we want to know. So when we discuss easy movement, spontaneous movement, movement in a favorable direction, we describe it as passive transport, happens automatically. And in the past, you've probably described this as moving down a gradient in biology, because usually we focus in the earlier courses on chemical gradients, right? So concentration, where is there a lot of something, where is there a little of something? Okay. So spontaneous movement would be down a gradient from an area of high to low, passive transport. Active transport takes energy, right? It's going to take usually that ATP that we just learned how cells make, right? And this is because this is a process that's hard, right? So we're trying to go and pack extra molecules into a place there's already a lot of them, usually in active transport. So we'll describe this often as going up a gradient, right? Just the way you would have to roll something up a hill by pushing really hard, you're going to have to expend energy to do active transport. This isn't going to be a spontaneous process. And in a future class, future session, we're going to get into the details of the different types of passive and active transport. But first, we're going to get a little more detail on specifics of what's going to be spontaneous versus not spontaneous. Because while we simplify it earlier in the curriculum and focus on concentrations, it's actually more complicated. And in particular, we also have to think about electrical charges. And then we have to think about what do we do if our information about electrical charges and chemical concentrations are in conflict, and we have kind of a question about which one's going to win out. So we are going to be combining chemical forces and electrical forces into something called the electrochemical force. And when we talk about passive and active transport again, we're going to realize that to truly determine what's spontaneous or not, we don't need to know only the concentration. We need to know something about the total force on a molecule, which also has this other component. So you reviewed the chemical driving force. It's hopefully familiar to you. So chemical driving forces are going to happen on any particle, any molecule. That's not going to be true for electrical forces. That's going to be only some particles. But a chemical driving force, that's going to happen on glucose, it's going to happen on an ion, it's going to happen on anything itself. So what that is driven by is really a system trying to reach equilibrium, which my chemistry friends might not like it, but when we think about equilibrium, as biologists, we're thinking about everything kind of spreading out, right? Everything kind of trying to be evenly distributed all over the place. Okay. So in order to do that from that basis, with the chemical driving force, we're going to see that the natural movement, the spontaneous movement, the favorable movement with respect to a concentration gradient, you want everything evenly spaced. You can start moving some stuff from areas where things are closely packed, are areas of high concentration, to areas where we have things loosely packed, are areas of lower concentration. So we're going to think about chemical driving forces as going from high to low concentration. This is where you left off in the material that you were reviewing on Friday. We started to intro this idea of the electrical driving force, which I expect to be new to most or all of you. Okay. So when we're thinking about the electrical driving force, this is not going to happen to every single molecule. Like, we think about glucose a fair bit, electrical driving force, glucose doesn't care about this at all. Okay. Electrical driving force is going to pertain specifically to ions. Okay. So the electrical driving force acts on ions. So does the chemical driving force. So we now have to combine two things. But if you're not thinking about an ion, you can ignore the electrical driving force, which means you can also ignore the electrochemical driving force because we don't have that additional component. So if I'm asking you about glucose or oxygen or carbon dioxide, you don't have to think about that. You don't have to worry about it. But ions are super, super important in your body, and they're super, super important to the function of nerves, which is our next unit. So we do unfortunately have to understand how ions behave and how this electrical force behaves in the body. Okay. So basic terminology. An ion is a charged particle. So common ones we'll see are sodium ions, potassium ions, chloride ions, calcium ions, and in ANP2, you'll also see bicarbonate ions. And that might be the full list of ions that you'll have to deal with in this course. They're certainly the ones that rise to the top of mind. Mainly, we're going to be thinking about sodium and potassium all the time. Like all the time, we're going to be thinking about sodium and potassium. So those are the ones to really focus on. Okay. So we're saying charged particles. So we got two flavors of charged particles, right? Because this is due to a bond between two atoms or more, where one of those atoms completely takes control of an electron from the other atom, right? So that's how an ionic bond forms. And if you have it on a table in the air, well and good, you might have a crystal, right? Table salt, NaCl, sodium chloride, is a crystal, if I put it on the table here, right? But when you put ionically bound compounds in water, they dissociate, so they separate. And that's when we start to have to think about the fact that we have these different charges on different ions. Okay. So we're going to have positively charged ions. Positively charged ions are called cations. So both sodium and potassium are cations. They have positive charges. So is calcium. Anions have a negative charge, so they're the ones that got an extra electron. Common example of an anion that we'll see are chloride ions. So Cl minus. Chloride ion has a negative charge. So depending on the charge, positive or negative, different ions are going to behave differently. That value, that sign on the charge matters. Okay. The other thing to know, other than the ions, right, so those are the particles we're going to be tracing. We also need to know a fact about the cell. The thing about the cell is that a cell actually also has a charge, kind of. No, a cell does have a charge. It's due to ions, but we can think of it as being part of the cell for our purposes. Okay. So we're going to see something called the membrane potential. You can think of that membrane potential, kind of the charge on the cell. So it's abbreviated Vm. Anytime you see Vm, that's the membrane potential. We're going to be careful because we are going to see MV as well, millivolts, which is a unit sometimes on the membrane potential, but Vm is the membrane potential itself. What the membrane potential is reflecting is that some cells are going to have lots of cations, lots of positive ions inside them. Some cells are going to have lots of anions, lots of negative ions inside them. And that means that those cells, when you compare them to the extracellular fluid, you're going to have different charges inside them versus outside them. Okay. So this creates the membrane potential. When we add together all the positive and negative charges inside the cell, all the positive and negative charges outside the cell, and compare them, we can say the inside of the cell is at negative 70 millivolts. That's its membrane potential. I would tell you that it's got 70 millivolts less of charge inside that cell versus outside. So we're going to see that happen. We're going to see membrane potential change, especially as we begin to talk about the nervous system and neurons. So we have this charge separation. It's actually going to act a little bit as a source of energy for the movement of the cell. So that membrane potential with its charge inside the cell is going to react with those charges on the ion. And we'll be thinking about how that works. So it's going to have a sign, positive or negative. It's also going to have a magnitude. So magnitude, we're thinking the strength of that force. We're usually going to see it measured in millivolts. Okay? And when I say it has a polarity, that's a bit about the plus or minus sign, right? Either positive or negative. And our reference point is inside of the cell versus the outside of the cell. So we give a membrane potential of negative 70. We're saying negative 70 is the charge inside the cell relative to outside the cell. Okay. And I keep using this negative 70 example because when we talk about neurons, that's going to be our baseline. We're going to see lots of changes from negative 70, but if you're starting out trying to think about the easiest, most normal example that you'll see over and over again in this course, first kind of thing to understand is going to be that value. All right. So as we start this next bit, I want you to go ahead and draw yourself a cell. Okay. And I want you to draw a cell that has high sodium concentration outside the cell, a low sodium concentration inside the cell. You're going to practice using some of our terminology. So you're going to label the ECF, you're going to label the ICF, and you're going to identify what the solute is. Okay. Then you're going to use your understanding of chemical driving forces to tell me which way our chemical driving force, the CDF, is going to point for the sodium. So how is this concentration gradient pushing or pulling on our sodium ions? Bonus, if you get only to number 2, we may move on at that point. But the next piece is going to you're going to want to be able to think about, certainly by the time we get to the exam, is if we have a sodium ion leave the cell, is that going to be active or passive transfer? Is it going to be easy or hard? Is it going to take energy or not? And you want to think about, can sodium cross that cell membrane? I'll give you a couple minutes to do this, to draw your cell and at least get through this chemical driving force bit. And I'll draw it with you. Tack on this idea of the electrical driving force and start to think about how we combine chemical and electrical forces on our planet. another couple seconds and I'm going to start drawing with you to make sure we're all on the same page here. Leaving down in these bullet points at the bottom, if you're not done, those pieces of this that we're trying to draw onto our cell. I'm going to start by labeling our extracellular fluid, intracellular fluid, and the solute. So extracellular fluid, outside the cell. Intracellular fluid, inside the cell. Okay. So those are two locations that we're thinking about. And our solute, who wants to tell me what our solute is? Yeah, perfect. Our solute are the sodium ions. Okay. So we know that for our solute, our sodium ions, we can see already that sodium is a cation, right? So this positive charge on it. Okay, so we've created a high concentration outside the cell. We're just gonna write high. We're gonna be a little lazy right now. Not gonna make up a number. High concentration here. And we have a low concentration here. So somebody else volunteer and tell me what direction are we gonna have movement of sodium ions? If we're just thinking about chemical driving forces, what's the force on this sodium ion? I'm going to point out that we would have sodium ions both inside and outside the cell, right? I only wrote them on the outside, but we got some number inside, some number outside. Yep. Yeah, perfect. So we're going from high to low, high concentration to low concentration, and that's our chemical driving force. Cool. So that's already half of our electrochemical driving force. Okay, so this is this one side. Okay. So if we think about active and passive transport tacking onto this, sodium trying to leave the cell with this knowledge that we have here, do you think that that's going to be active transport or is it going to be passive transport? Right, active transport, because we're going against our force, and to fight against the force, we need energy. So we need active transport. Okay. So the membrane, as I've drawn it here, imagine this dashed line is phospholipids. So this is the cell I've drawn, phospholipids. Is sodium going to be able to get out of the cell? See some head shaking, which is great. The answer is no. In this cell, as I've drawn it, sodium would not be able to cross the cell membrane because I didn't draw any proteins on, right? So in order for sodium to actually be able to follow the direction that it wants to move, we need to embed some type of transmembrane protein that's able to transport sodium, either to let it into the cell, or if we want to do that active transport and let it go out of the cell, right, we need one going that direction, and we need our ATP. Cool. That's what we should be able to understand to this point. So, basic principles of our electrical driving force. So, just like when you learn about ionic bonds, we're going to see that opposites attract, right? And so when I say that opposites attract, I mean they're like magnets, right? So if you have a positive charge, right? And let's think about the table salt, right? So a typical example of an ionically bound compound is sodium positive, chloride negative. And the reason that that sticks together until we drop it in water is we have a positive charge and a negative charge acting like magnets pulling towards each other. So this is going to be important for understanding the electrical driving force, but we're going to be thinking about it on a larger scale. We're going to be thinking about collections of ions. We're going to be thinking about the collections of charges that make up the membrane. But this basic positive and negative come together, it's gonna work the same. Okay. So opposite charges attract. The other thing to realize is that like charges repel each other. So if we have two sodium ions next to each other, both with positive charges, they're going to push away, right? So they are each going to push away. I might pick a different color. That's okay. Okay, so they're pushing away from the like charge. So positive and positive, push apart, negative and negative, push apart. Just like if you have a magnet with two sides and you try to force them together, you can't. There's a force stopping you, right? That's this repellent that we're experiencing. Okay. So that happens with our ions and our membrane potentials as well. So for our direction on our forces, when we're thinking about the electrical driving force, which is the next piece that we're adding on to our understanding of chemical driving force, we're going to need to know the polarity of the cell, which I mean, is that membrane potential positive or is it negative, right? So is it plus or minus inside the cell? And I'm going to need to know, do I have a cation or do I have an anion? Do I have a positive ion I'm looking at? Or do I have a negative ion I'm looking at, right? This is because we're going to be trying to figure out, do they repel each other or do they attract each other? Okay. So without doing any numbers right now, although we will have to look at numbers, Vm is our membrane potential. So if I tell you that we have a negative membrane potential, put that in parentheses so we can see it. Okay. A sodium ion, right, with its positive charge, okay, is going to be drawn towards the inside of the cell and that negative membrane potential. But if I have a chloride ion, okay, chloride ion with that negative charge, we're looking at that same membrane potential that's negative. Our chloride ion is going to try to run away. It's going to be repelled. It's going to be pushed away from that same charge, that negative charge repelled. So that's the fundamental thing that we're looking at when we're looking at the electrical driving force. If we're looking on its own, all we have to look at is our charge on the ion, our charge inside the cell, right? And we already know the direction just from that. They're the same, they're pushing apart from each other. If they're opposite, we're going to have movement, or we're going to have a force into the cell towards that opposite charge. Okay. So here we see an idea of how we would have a buildup of a membrane potential in the first place, like how we would get, for example, -70 inside the cell as our membrane potential, or we'll see neurons go up to +60. Right? What we're looking at is a separation of charges where we see some number, we could count them, cations versus anions inside our cell versus outside our cell. Okay, this was ECDF, so blue was outside the cell. Inside, we have lots of negative charges. Here, lots of anions. And this separation of charge, separated by a membrane, right? So the membrane, nothing can cross it, it's charged unless we let it, right? So that's why we refer to it as a separation of charges, right? So you can see negative and positive are being attracted to each other here on opposite sides of the membrane, but they can't get across because of that thick, non-polar hydrophobic layer inside the lipid bilayer of the cell membrane. So the separation of charges means that on net, right? So if we add them all together, subtract them out. On this side, we have more negative charges than we have positive charges, especially when we compare it to this side. We've got more positive charges. So this is how a membrane potential develops. And that's what we mean when we say we have a membrane. So for our electrical driving force, that we need to pay attention to the polarity of the cell and the charge on the particle, right? So this is just in book form, prettier pictures, what I just drew with my scribbles, okay? All right, so here we see that if we're looking for the direction of our electrical driving force on a positive ion, a cation, if we've got a negative membrane potential, right? So if I wrote Vm equals -70, positively charged ions, their electrical driving force, or EDF, as we will frequently abbreviate it, is going to be into the cell, drawn towards that opposite charge. And the opposite happens for negatively charged ions. They're going to be repelled from that collection of negatives inside the cell. So an anion, an electrical driving force, is going to push it out of the cell if we've got a negative charge inside, if we have a negative membrane potential. Okay. So you can ignore pretty much everything else other than these signs on our ions and our membrane potential if all you're trying to figure out is the direction of the electrical driving force. Okay. So whenever you see a question about the driving forces of any flavor, what you're going to want to pay attention to first is like, which driving force are we actually asking about? Chemical, electrical, or the combined electrochemical? Okay. If it's either chemical or electrical on its own, there's lots of stuff you can ignore. Okay. Now, if we want to figure out how powerful that electrical driving force is, we need to actually look at the numbers a little bit. Okay. So the magnitude of that force, how big it is, how strong it is going to depend on how negative or positive that membrane potential is. So how big the separation of charges is when we're comparing the inside of the cell versus the outside of the cell. Okay. So if we have a bigger separation of charges, right? So in this case, a more negative membrane potential is going to mean a bigger force, a bigger, in this case, pull, because we have a negative membrane potential and a positive ion. And you can see that in the size of these arrows, right? So they're trying to tell you bigger arrow, bigger force. Okay. So we can make the force bigger, the magnitude of the EDF bigger by changing the membrane potential of the cell. Or we can look at the other side of this relationship. We can look at that charge on the ion. Okay, so the amount of charge on the particle or the valence on the particle, we'll sometimes refer to it as, is also going to have an influence. And really when we say that in biology, what we're pointing out is that calcium isn't just calcium plus, it's calcium 2 plus. Okay, so it has 2 missing electrons, right? And this would happen to some other ions too. This is the one we'll see involved in neurons. This is the one we'll see involved in heart. Okay. So if you have a bigger charge on the ion, that also creates a stronger force. So the 2 pictures you're comparing for this amount of charge on the particle are A versus C. So you can see this kind of double charge on this cation created a slightly larger force, even given the same membrane potential. So that's how we can change magnitude of electrical driving forces. So before we start to combine this stuff, any questions about the electrical driving force or the membrane potential on its own? You may have questions later as you continue to reflect, and that's cool. But we'll keep powering through for now. Okay, so I'll ask you a question that I can see your answers to. Okay. All right, so you're gonna start by telling me what direction that electrical driving force is going to be for a sodium ion if instead of having a cell at -70 millivolts, we have a cell at +50 millivolts. I'm gonna do this kind of quick so that we get to the combined force by the end of class today, at least intro it, because I suspect it will be appearing on your SI worksheets tonight. Now let me take a look. Hopefully we're on the same page. Cool. Yeah, we are on the same page. Excellent. All right, so we have a positive membrane potential inside the cell, and we're looking at a sodium ion. They repel each other, so the sodium ion is running away from that positive charge. So the EDF, the electrical driving force, is going to point out. Great. Okay. Great. So if we have a situation like we've been thinking about, if we have a membrane potential of positive 50, and we're looking at a positive sodium ion, okay, and we say, as you all just did, this means those sodium ions are being repelled by the electrical driving force. Okay. But let's say if we looked at the chemical side, if we looked at concentrations, right, we might still have a concentration where we have more sodium outside the cell and less sodium inside the cell. So that's the picture that you drew me when we did that little recap, right? So we might have a chemical driving force in the situation pointing inside the cell. And this is where we're going to have to think critically in order to figure out what direction our electrochemical driving force. So electrochemical driving force is going to be the ECDF, right? So in this situation, we kind of got a question, right? So we've got two opposing forces on any given sodium ion. Right? One of them pulling that sodium ion into the cell, the other is repelling the sodium ion outside of the cell. And we need to kind of make sense of that. We need to figure out whether this push or this pull is stronger if we want to figure out on net, so like total, what direction our sodium ions are going to be flowing. So that's the point of the electrochemical driving force. Okay. So when we talk about the electrochemical driving force, what we're talking about is the total force on the particle, right? So the total force on an ion, your sodium ion, you've got some direction that your chemical driving force is telling you to go. You've got some direction that your electrical driving force is telling you to go. But you're only actually going to go in one direction, right? So we got to figure out which of those is stronger, compare their directions, compare their magnitudes. So we can think of this electrochemical driving force as just adding together that chemical driving force and that electrical driving force. Right? Although when I say adding together, we're going to choose the direction right, into the cell or out of the cell. That's our positive direction. And then the opposite direction is going to be our negative direction. So sometimes you're going to do subtraction, what I'm saying to you. But if you draw arrows, it's going to be relatively simple. So I recommend for these types of questions, it's really helpful to draw them out. Okay. Cool. So when we have a situation that our chemical and electrical forces are in the same direction, we don't really have a problem, right? So if we have a situation where we've got a cell, let's say we got a sodium ion, okay? Let's say well, we know if we have a negative charge inside the cell, let's say we're at negative 70 for our VM, right? Our electrical driving force is going to be into the cell, okay? And if we want to make a chemical driving force in that same direction, right? We're thinking high concentration of sodium outside, low concentration of sodium inside, right? We can imagine just adding them together tail to tail without even looking at the numbers, right? So if I take chemical driving force and add electrical driving force, now I have one big long arrow. When I added them together, that's our electrochemical driving force. So situations like this are going to be relatively simple because you don't have to figure out which one's stronger because they're going in the same direction. So we're just going to have a big force in that direction. If we wanted to talk about its size, we would have to add them together. But we can just kind of hand wave this as really strong if these are both strong enough. Okay. Now, we're going to skip this question for now. We'll come back to it as a review question next time. I'll make sure that we get to what happens if we have opposite directions. Okay. So this is the one where we have a problem. Okay. So say we have a cell. We've got a chemical driving force going into the cell. And we've got an electrical driving force going out of the cell. Right, as we drew in our sodium example, right, we have two conflicting directions. Okay. Now to determine our electrochemical driving force, so our combined force, what we're going to do conceptually is still add these two together, right? But they're in opposite directions, right? So we're going to essentially have parts of this canceling out. Right, so if we imagine, right, looking at this visually, this is how big our chemical driving force is. Right, so if we're adding together, these two parts of the force cancel out, and we're left with this chunk. Okay, so in this case, even without any numbers, just looking at the arrows, we'd know that we have electrochemical driving force pointing out of the cell, but it's smaller than that total electrical driving force was in the first place, right? So we're pointing the same way as the electrical driving force, but we're kind of little because we have this chemical driving force pulling against it. Okay. So we're going to be subtracting the larger force, subtracting the smaller force from the larger force in the case that they're in opposite directions. But again, I think drawing them is really the easiest way to do it because then you don't have to think, are you adding, are you subtracting? Okay. Now, it's important to realize that sometimes we're going to have a particle that's not transported across a membrane, even when it's permeable. One of the times that's going to happen is when we have equal forces in opposite directions, right? Someone's pulling you one way, and someone's pushing you the other way, and they're both the same strength. Nothing's going to happen. You're just not going to move. So we're going to have a number that sums all this together that you can look at, even if no one explicitly tells you this is the concentration, this is the membrane. You are going to need the membrane. You're not always going to need the concentration numbers to figure this out. Okay. This is because for every ion, we're going to have a membrane potential where we're at equilibrium. The chemical driving force, one direction, is exactly equal but opposite to the electrical driving force. So in this case, nobody's pulling you in any direction on net because they're completely canceling each other out, right? They completely cancel each other out here. Okay. Now, because this partially involves the chemical driving force, which has to do with concentrations of that ion specifically, it's going to matter what ion we're talking about, right? Okay. And the way we're going to note down this special membrane potential, right? We're going to have an equilibrium potential is what we're going to call it. And the subscript is going to correspond to the specific ion we're talking about, right? So we're thinking about the force on potassium, chemical driving force on potassium, electrical driving force on potassium, right? So if I tell you that the membrane potential of potassium is -94, I'm telling you that potassium ions will move around, move until that inside of the cell is at -94. And that's the point that the electrical driving force and the chemical driving force cancel each other out. So just by using this number, you can figure out where the electrochemical driving force points, right? Because if we imagine here, let's say the cell, instead of a membrane potential, let's say we're at negative 60 for our VM. Right. Just with this information, we know potassium ions are going to move, they're going to move, they're going to move until the cell gets to negative 94. And potassium is positive. I mean that to get to negative 60, we're going to have potassium, or sorry, say it the reverse way. If we're starting at negative 60 and we need to get to negative 94, this equilibrium potential, this means we have to have potassium ions leave the cell. So we have to take positive charges out, subtract them away until we get to this negative 94 number. And we'll talk about other ways that you can think about this and solve these types of problems next time. But honestly, I think this is the easiest way. Just look at that equilibrium potential, figure out, do you move positive charges in or out to get to that number? And presto, you have the electrochemical dragon force.